Okay. Now in the previous session, now this is a question we are taking, question number 7 in your handbook. The impulse response of the LTI system is given to you, and he is asking to find type and order. Now see here, now this is the impulse response which is given. For finding type and order, first we need some transfer function. But just now I am saying, when there is an impulse response for a linear time invariant system, then you know the transfer function definition. What is the transfer function of a linear time invariant system? The transfer function of a linear time invariant system is defined as Laplace transformation of impulse response with all initial conditions are equal to 0. Therefore, use that particular definition and find the transfer function first. The transfer function of a linear time invariant system is defined as Laplace transformation of impulse response with all initial conditions are equal to 0. The transfer function of a linear time invariant system is defined as Laplace transformation of impulse response with all initial conditions are equal to 0. Therefore, which is nothing but the Laplace transformation of what is impulse response? The impulse response which is equal to minus t into e power minus t plus 2 into e power minus t. Now the transfer function which is nothing but minus 1 by s plus 1 whole square plus 2 by s plus 1. This is the transfer function. Therefore, the transfer function which is equal to s plus 1 whole square, now this is minus 1 plus 2s plus 2. Now this is the transfer function for a linear time invariant system is defined as Laplace transformation of impulse response. Therefore, which is nothing but 2s plus 1 by s plus 1 whole square. Now this is the transfer function definition. Now see here, now this is the transfer function for a linear time invariant system. Therefore, for a linear time invariant system, the transfer function is nothing but the Laplace transformation. Therefore, which control system it is? Now obviously this is a closed loop control system transfer function. Once if it is a closed loop control system transfer function here, then your job is very easy. Now if this is a closed loop control system transfer function, now we can find directly order. If this is a closed loop control system transfer function, then what is the order? Now there are two closed loop poles and the highest power in the denominator polynomial is 2. Therefore, order equal to 2. Now the highest power in the denominator polynomial is 2 and the highest power in the characteristic equation is 2. Therefore, this order equal to 2. Then we will find order. This is the closed loop control system transfer function. Then we want to find type. You already know that. For finding the type, now we want to go for open loop control system. You know that this is the closed loop control system transfer function. Now I want a open loop control system transfer function. Then how to get the open loop control system transfer function from the closed loop control system? You know that the numerator equal to numerator and the denominator equal to denominator minus numerator. So this is nothing but 2s plus 1 by 1 2s cancel, which is nothing but s square. Therefore, there are two open loop poles available at origin. Therefore, type equal to, type which is equal to 2. Now this is now the question number 7. Now what is given is find type and order by considering the impulse response, and this is the solution for that. Now your workbook, classroom workbook. Now question number 8. Now question number 8. Now what is that question is? Now the impulse response of a linear time invariant system is given as sin t. The impulse response, your workbook, classroom workbook, question number 8. The impulse response of a linear time invariant system is sin t, and what he is asking is the impulse response of a linear time invariant system is sin t, and he is asking find the differential equation related to that control system, to that LTI system. Now this is the question. What is asking? Now in our classroom workbook, question number 8 is the impulse response of a LTI system is given as sin t. Find the differential equation related to that LTI system. Now only one thing we know, that now the solution is, once if you know the impulse response for a LTI system, now first we want to find the transfer function. Now for a LTI system, the linear time invariant system, for a LTI system, impulse response is Laplace transformation of impulse response is nothing but the transfer function. Impulse response is given as sin t. Therefore, which is equal to Laplace transformation of sin bt, b by s square plus b square, b by s square plus b square. Now what is the transfer function? Now the transfer function, which is nothing but the Laplace transformation of output to the Laplace transformation of input, now which is nothing but how much we are getting, 1 by s square plus 1 square means 1. But in the question is mentioned where input is r of t and output is c of t is mentioned. Now input is r of t, output is c of t. So Laplace transformation of output c of s by Laplace transformation of input r of s, which is equal to 1 by s square plus 1. Now this is the transfer function which is given to you, and what he is asking is, for a linear time invariant system, impulse response is given. Now he is asking the differential equation related to that particular system. Therefore, then if I cross multiply this, if you cross multiply s square into c of s plus c of s, which is equal to r of s. S square into c of s plus c of s equal to r of s. This, then if you apply inverse Laplace transformation, then if you apply the inverse Laplace transformation, now inverse Laplace transformation of s square is d square c of t by dt square plus c of s inverse Laplace transformation is c of t, which is equal to r of t. This is the differential equation related to this particular LTI system. Once again I am saying, for an impulse response of a linear time invariant system is sin t, find the differential equation related to that system where input is r of t, output is c of t. This is the question. Now what is the solution? Now once if the impulse response is given, first you find the transfer function. The transfer function is nothing but Laplace transformation of impulse response with all initial conditions are equal to 0. Therefore, the transfer function is nothing but 1 by s square plus 1, but you know that output by input, but output is r of t is input, output is c of t. Therefore, c of s by r of s equal to 1 by s square plus 1. If I cross multiply and apply the inverse Laplace transformation, now this is the differential equation related to that particular LTI system. Is the question number 8 in our classroom workbook. Take a copy of this. Okay. Now, in your classroom workbook, question number 9. Now, classroom workbook, question number 9. Question number 9. In our classroom workbook, question number 9. Now, in our classroom workbook, question number 9, the step response of a system is, what is given is now, the step response of a control system, which is given as 5 minus 1 by 2 into e power minus 2t plus 8 into e power minus t. This is question number 9. What is given is the step response of the control system 5 minus 1 by 2 into e power minus 2t plus 8 into e power minus t. Then what is the question is, determine the system gain if the control system represented in time constant form. See here, the question is determine system gain if the control system represented in time constant form. Now this is the question which is given to you. Okay. Now see here. Now what is given? The step response is given. But we have one concept now. Once you have the impulse response, you can immediately find the transfer function or not? Yes. Therefore, once we have the impulse response, we can easily find the transfer function by using this formula. But in the question, he is not mentioning impulse response. Now, what is mentioned in the question? He is mentioning the step response. That's what now previously we just studied the conversion from one response to another response. Now here the question is mentioned step response, but I want the impulse response for easily finding the transfer function. Then you have some relations, use that relations and converting from one response to the another response. What is the response he is giving? Step response. What is the response you want? Impulse response. Then what is the relation? Yes, there is a relation. What is the relation? Now the solution is, now the impulse response, which is nothing but, the impulse response is nothing but derivative of step response. If you differentiate the step response, then you can get the impulse response. Therefore, what is the step response? This is the step response. Now if you differentiate the step response, 5 minus 1 by 2 into e power minus 2t plus 8 into e power minus t. This is the step response. Then if you differentiate, then this is the impulse response. Now differentiation of 5, which is equal to 0, minus 1 by 2 into minus 2 into e power minus 2t minus 8 into e power minus t. This is the impulse response. So minus minus cancel, 2 cancel, e power minus 2t minus 8 into e power minus t. This is the impulse response. This is the impulse response. Once if you get the impulse response, now you can get the transfer function. What is the transfer function? The transfer function of a linear time invariant system is nothing but, the transfer function of a linear time invariant system is nothing but Laplace transformation of impulse response with all initial conditions are equal to 0. Therefore, now by using that, then we can find the transfer function. What is the transfer function? Now the transfer function, which is nothing but, now the Laplace transformation of impulse response is nothing but Laplace transformation of, what is impulse response? E power minus 2t minus 8 into e power minus t. Therefore, which is nothing but 1 by s plus 2 minus 8 by s plus 1. Therefore, s plus 1 minus 8s minus 16 by s plus 2 into s plus 1. Therefore, minus 7s minus 15 by s plus 1 into s plus 2. This is the transfer function. But the question is not asking the transfer function. He is not answering the transfer function. What he is asking? He is asking to find the system gain, and he is mentioned if the control system represented in time constant form. Therefore, now if you see here, now this is the transfer function s plus z1, s plus z2 and so on by s plus p1, s plus p2 and so on, which means while looking this transfer function, this is 0 z1, this is 0 z2, this is pole p1, this is pole p2 and so on, which means that while looking this, now this transfer function, you can easily identify the zeros and poles. This type of transfer function is called as the transfer function represented in pole zero form. This is called as the transfer function represented in pole zero form. This is one way to represent the transfer function, the transfer function represented in pole zero form, because zeros and poles are available directly. This is one way to represent the transfer function. Then the another way is nothing but which is you already have an experience of this, the transfer function now, which is nothing but k into 1 plus st1 into 1 plus st2 into s power n into 1 plus sta into 1 plus stb, now and so on. But if you observe here this type of transfer function which are familiar for us. Now in this transfer function, while looking this, T1, T2, TA, TB are available directly. Here is Z1, Z2, P1, P2 are available. This is pole zero form. Then here T1, T2, TA, TB are available. Therefore, this way of representation is called as the transfer function represented. The transfer function represented in time constant form. This is called as the transfer function represented in time constant form. Now you read your question, then you have some idea. What is the question? Now the step response is given and determine the system gain k if the control system represented in time constant form. Now we have the transfer function. But see our transfer function, s plus 1, s plus 2 means s plus p1, s plus p2 means this is which form? Pole zero form. But the question is mentioned, determine the system gain k if the control system represented in time constant form. The time constant form. Therefore, but the question what we are getting is pole zero form. This is pole zero form. This is pole zero form. But I want the system gain if the transfer function represented in time constant form. Therefore, now you first converted this pole zero form to time constant form, then you compare and you can get the answer. Therefore, while you compare this pole zero form to time constant form, take all constants as common. If you take all constants as common, what happens? Now this minus 15 is taking as a common 1 plus 7 by 15 into s divided by 1 if you take it as a common, 2 if you take it as a common, 1 plus 1 into s, 1 plus 1 by 2 into s. Now this is the transfer function. Now you compare this one. Now 1 plus st1, 1 plus sta, 1 plus stb. This is nothing but 1 plus st is a time constant form. Now your transfer function is in time constant form, and compare and find the system gain k. Now this is the system gain k. Determine the system gain k if the control system represented in time constant form. Now this is in the time constant form. Then if you compare these two, now this is the system gain k. How much? Now this is the system gain k, which is nothing but minus 15 by 2, which is equal to minus 7.5. Now determine the system gain k if the control system represented in time constant form, right? Now this is the system gain k, and not only in this question number 9, not only the this is not a question, then there you can have some concept also. Now what are the different types of transfer functions? There are two types of transfer functions. It may be a pole zero form, or it may be a time constant form. You convert it from pole zero form to time constant form, or time constant form to pole zero form according to your situation. The question is mentioned time constant form strictly, therefore you convert into time constant form. Now this is k equal minus 7.5, but practically gain is always positive. Then this is actually the gain, and with the system time constant form, the transfer function is represented in time constant form. Take this one. Okay. Now in our classroom workbook, question number 10. Question number 10. A control system describes the differential equation. A control system describes the differential equation d square y of t by dt square plus 5 into dy of t by dt plus 6 into y of t, which is equal to x of t. The control system describes the differential equation d square y of t by dt square, which is equal to 5 into dy by dt plus 6 into y of t equal to x of t. Now let x of t is a rectangular pulse as given as x of t is a rectangular pulse is given as let x of t is a rectangular pulse let x of t is a rectangular pulse is given as, then assume all initial conditions are equal to 0, then he is asking Laplace transformation of y of t is dash. Now which means that now what he is asking is Laplace transformation of y of t means what? Laplace transformation of y of t is nothing but y of s only. In order to confusion, then he is giving Laplace transformation of y of t is dash. What is Laplace transformation of y of t? Laplace transformation of y of t is nothing but y of s is equal to dash. That is the question. So Laplace transformation of y of t means y of s. Y of s is how much? Y of s is how much means, then you apply here. Then you apply the Laplace transformation. Apply Laplace transformation. Laplace transformation of second order differential equation is s square into y of s plus 5 into s into y of s plus 6 into y of s, which is equal to x of s. Now then if you take y of s as a common, then if you take y of s as a common, s square plus 5s plus 6, which is equal to x of s. Y of s, if you take it as a common, s square plus 5s plus 6, then what is y of s? Then this is the y of s, which is equal to x of s by s square plus 5s plus 6. What is x of s? X of t, which is equal to 1. If x of t which is equal to 1, then what is x of s? X of s, which is equal to Laplace transformation of 1 is 1 by s. Therefore, if I take x of s equal to 1 here, now this is nothing but 1 by s into s square plus 5s plus 6. Now this is the Laplace transformation of y of t, y of s. Now this is also there in option number B. Options are also given. Now this is option B, but most of you are thinking that this is the correct answer, but this is 100% wrong. This approach is wrong. This is wrong answer. But this is there in the option B. Now if you go for this option, this is wrong. Option B is wrong because this concept is also wrong. Now just think why this is wrong. Okay, this is wrong. Option B is wrong. This is also wrong. Because now this x of t, you don't take it as 1, because what he's saying? He's saying that this x of t is this is a rectangular pulse. What he's saying? X of t is a rectangular pulse. If it is a rectangular pulse, it is having some characteristics, no? Now this is x of t is a rectangular pulse. Now what is a rectangular pulse? Now x of t is a rectangular pulse. It is having some pulse width. What is the pulse width which is given? Yes, this is a pulse width of how much? 2. Now, what is the pulse height or amplitude? This is 1. This is x of t. Don't take it directly as 1, because this is, he says that x of t is a rectangular pulse. The question is mentioned, this is a rectangular pulse. X of t is a rectangular pulse. Therefore, now I want x of s. What is x of s? Then if you want to find x of s, now x of s equal to Laplace transformation of x of t e power minus st into dt. Therefore, integration this is a positive signal, 0 to infinity, x of t equal to 1 into e power minus st into dt. Therefore, which is equal to minus 1 by s e power minus st over the limits 0 to infinity, which is equal to minus 1 by s e power minus infinity minus e power 0 equal to 1. Therefore, this is 0 to 2. This is 0 to 2. Now this is minus 1 by s into e power minus, upper limit is 2, lower limit is 0, e power 0 is 1. If I take this minus as a common, this is nothing but 1 minus e power minus 2s by s. This is x of s. Then what is our question finally? Laplace transformation of y of t is Laplace transformation of y of t, which is nothing but Laplace transformation of y of t, which is nothing but y of s, which is nothing but y of s, which is nothing but x of s by s square. Then what is x of s you are getting? X of s, which is nothing but 1 minus e power minus 2s by s into s square plus 5s plus 6. Now this is Laplace transformation of y of t, which is equal to y of s. This option is the correct option, and that is nothing but option A. Now, question number 11. Question number 11 in our workbook, classroom workbook, question number 11. By considering the control system describes the differential equation, a control system describes the differential equation as a control system is described with the differential equation d square y and tan into dy by dt plus 5 into y of t equal to 12 into 1 minus e power minus 2t into u of t. Now this is the differential equation which is given to you. Now he says that where y of t is output, this y of t is output and this u of t is input. Now what he is asking is determine the response at t tends to infinity. What is the question? The question is the response. Determine the response means output. The response at t tends to infinity is dash. This is the question. Now this is question number 11 in our workbook. Now the differential equation of a control system is given where y of t is output, u of t is input. The question is the response at t tends to infinity is equal to dash. Therefore can we write like this, d square y of t by dt square, which is equal to plus 10 into d y of t by dt plus 5 into y of t, which is equal to 12 into, if we multiply it with this u of t, 12 into u of t minus 12 into e power minus 2t into u of t. Now if I apply the Laplace transformation, now the Laplace transformation is s square into y of s plus 10 into s into y of s plus 5 into y of s, which is equal to 12 into Laplace transformation of u of t is 1 by s minus 12 into Laplace transformation of e power minus 2t is 1 by s plus 2. But in frequency domain, the mathematical analysis is simple. In frequency domain, we can easily solve the question. That's why I converted into time domain to frequency domain. Therefore, if I take 12 as a common here, I'll take LCM s plus 2 minus s by s into s plus 2. And if I take y of s as a common here, s square plus 10s plus 5. Now see here, then this s is cancelled. Then what is y of s here? Y of s, which is equal to this s is cancelled. 12 into 2, 24 by s into s plus 2 into s square plus 10s plus 5. Twelve into 2, 24 by s into s plus 2 into s square plus 10s plus 5. This is y of s. But what he is asking, he is asking the response at t tends to infinity. T tends to infinity means what? That is in time domain, am I not? But what we are having here, this is in frequency domain, but I want in time domain. Now see here, before we want to solve that, then I want to take one important formula here. Now limit t tends to infinity f of t. If I take limit t tends to infinity f of t, we know that what is s? S equal to sigma plus j omega. Assume real part equal to 0. If you assume real part equal to 0, s equal to j omega. S equal to j omega. If s equal to j omega, omega equal to 2 pi f, and we can write like this, j 2 pi f. Frequency and time is inversely proportional. Now see here, therefore this frequency and time is inversely proportional. Therefore limits t tends to infinity f of t, which is nothing but when time is tends to infinity, therefore this frequency s is tends to 0, s into f of s. This is one of the property of the Laplace transformation, which is nothing but when time is tends to infinity. Time is tends to infinity means the last value, final value. This is one of the property of the Laplace transformation, which is called as final value theorem. Final value theorem. And in the same manner you can find like this also. Limit t tends to 0 f of t. When time is tends to 0, when time is tends to 0, frequency is tends to infinity. Therefore, limit s is tends to infinity, s into f of s. Now, this is when time is tends to 0 means it is starting stage. Therefore, this is nothing but the initial value theorem. This is the initial value theorem. This is the initial value theorem, and that is the final value theorem. Therefore, now you see here that the response, what is the question? Now you go to the question what he is asking. Response. Response means what? Output. Response at t tends to infinity. The response at t tends to infinity, which means that output at t tends to infinity. Output at t tends to infinity. Therefore, now what is output here? In the question is mentioned output is nothing but y of t. Y of t at t tends to infinity. Now, from the property of the Laplace transformation, can I write like this? Limit t tends to infinity y of t, which is exactly equal to s tends to 0, s into y of s, which is equal to s into, what is y of s? Y of s is nothing but this one, 24 by s into s plus 2 into s square plus 10s plus 5. Therefore, and substitute s tends to 0. Therefore, this s and this s is cancelled and substitute s tends to 0. If you substitute s tends to 0, 24 by 2 into 5, which is equal to 24 by this 0, this is 0, now this is 0, 2 into 5, 10, 24 by 10, which is nothing but 2.4. Therefore, what is that? That is nothing but finally what is asking. This is nothing but a final value only directly. This is 2.4. Means what he is asking directly what is the final value. This is the final value. The time is tends to infinity. The response means output. Output means y of t. Y of t at t tends to infinity means then in time, in frequency domain, our analysis is easy. That's why in the question first I want to convert into frequency domain. Then our solution is very simple. And these two are also the important formulas, which is nothing but one is final value theorem, another one is initial value theorem. This is the response at t tends to infinity. Yes, which is equal to actually sigma plus j omega. Assume real part equal to 0. Therefore, yes, which is equal to j omega. J omega is nothing but 2 pi f, which is equal to 2 pi f is 1 by. Now, these are the two important formulas, and this is the question what he is asking. Okay. Now this is your question number 11, and based on that, these two formulas also, which is very useful to you, and this is the initial value theorem and final value theorem, which is also very useful. Okay. In the next session, we will see the further analysis of the control system in the basic portion itself. We will see in the next analysis.